Hey everybody, today we are going to finish up activity 2 in geometric sequences with talking about our lovely infinite geometric sequences. So we're on page 27 today and we're going to talk a lot about does a sequence converge or diverge for our geometric sequences, and we're also going to talk about finding the sum of an infinite geometric series. Okay? Now, this lesson starts off referencing back to lesson 2.1, our lovely Shelley's seashell experiment. And basically what they're asking in number 1 is, as these values increase here, what is going on with our hypotenuse lengths? Well, as these values get bigger, notice our hypotenuse lengths are actually getting smaller and they're approaching 0. While they'll never get there, they'll just get infinitely close to it. And basically what's happening with those is that our series is converging towards 0. It's going towards a specific number, versus diverging where it doesn't come towards a specific number. It either bounces between two numbers, never approaching just one, or it increases or decreases without bound. It goes really, really high towards infinity or really, really low towards negative infinity. Now, some ways to test these out. Does it converge versus does it diverge? I would say there are two useful methods. The first is the plug and chug mentality. What I mean by that is up here, for instance, we have this table of values. We plugged these values in and we're able to calculate them so we could see as this pattern increased, our values decreased. Right? That's method 1. The other method that is often quicker, depending on if you have the formula or not, is graphing, right? And especially with having these explicit formulas for our geometric sequences, we can graph and see, are they in fact converging or diverging towards a specific value. So for this Shelley seashell design, we talked about a couple times in both lessons about how this is our explicit formula. And if we graph that, which I did on Desmos, you're going to see that it does in fact converge towards 0 graphically as well. It's never going to quite hit 0. It's just going to get infinitely close to it, right? Well, we also have some other patterns here that we're going to want to look at. And we're going to want to decide, okay, are these values converging or are they diverging towards something specific? I'm going to choose to look at 3 of these. Let's look at 3. Let's look at 4. And let's look at 5. And we'll talk about the others later. Now, in 3, our R value here is -1, because if we can divide these two consecutive terms, 4.2 divided by -4.2 gives us that common ratio of -1. And basically what's happening if we were to graph this, these guys would be bouncing back and forth along here. They'd be oscillating back and forth, which means officially they're diverging, right? Because they're not going to a specific value. They're bouncing back and forth. Now, number 4, if we look for that common ratio, if we divide -1/3 by +1/3, or excuse me, +1/9, what we're going to see here is that when we divide these two values, this time our R value is -3, right? Or 9 divided by -3, -3. And this also, again, is diverging. Now, the reason being on this one, if we look at the pattern here, these are, again, bouncing back and forth between being positive and negative, and they're getting really, really big in the positive direction, really, really small in the negative direction each time. So, again, it's diverging. The last one here, if we try to calculate our R value, if we take term 2 divided by term 1. What we're going to see is 25 divided by the square root of 5 divided by 25 simplifies to be 1 over square root of 5 or square root of 5 over 5 if we rationalize, okay? Now, this value here, these values are actually going to converge because we went from 25 divided by the square root of 5. We have 25 divided by 5, which is 5. And we keep going, we're getting down to 1. Again, these are actually converging towards 0 each time as well. Now on your own, take a moment to check out these remaining sequences, 1, 2, 6, and 7, and determine which of these converges, which of these diverges. Well, what you should have noticed here is that our first series here, our R value is 10, this diverges. Our R value here was 1/2 or 0.5, this converged towards 0. And down here for 6, the R value was 0.01 or 1/100th. This converged to 0. And last but not least, in 7, our R value was the square root of 2, and this one diverged. So at this point, are you noticing a pattern between the ones that converge versus the ones that diverge? Well, hopefully something you notice as you flip towards page 28, we'll skip over 4 to save some time, is that when we had these absolute values of R that were less than 1, so the ones that were like 0.5 or 0.01, these ones were the values that were sequences converging towards 0. Sequence converges towards 0. On the other hand, if we had R values that were either equal to -1 or that absolute value of R was bigger than 1, though that's where our series were diverging, right? So we had when it was -3 or when it was equal to -1 and oscillating, those were the ones that were diverging, okay? And that's going to also hold true kind of moving forward with our partial sums. So if we start saying if there's a connection between the sequence itself and the partial sums, will these continue to converge or diverge? So this first one from the last page, this sequence here was a diverging sequence. This original sequence diverged, right? It was getting infinitely big. And if we look at the partial sums, however, is there a if we look at the sum sequence, is there going to be a pattern as well? So if we add up the first term, the first 2 terms, the first 3 terms, what we're noticing is that these values also continue to get bigger as we find the sums of this sequence, and it's also continuing to diverge, right? This is also a sequence that's going to diverge. However, in a sequence like number 2 that was a converging sequence, right? It converged to 0 on the last problem. We had this converging sequence, and same thing, if we look at the partial sums, add up the first term, first 2 terms, add up the first 3, first 4, first 5. What we're noticing is while this is getting bigger as we move down the line here, they're getting bigger much slower so that it seems to be approaching 200. We're getting really close to approaching that. So what we're seeing here is this is also going to converge, but in this case, it's going to converge towards 200, okay? And we can test this out as well with the oscillating sequence. We said in this last problem, this one was a diverging one because it bounced back and forth. So this one also diverged. And this time, add up the first term, add up the first 2, add up the first 3. What you're going to notice is this is going to continue to oscillate. So it's again going to continue to diverge. So right now what we can see is that if a sequence converged originally, the sums are also going to converge. And if the sequence diverged originally, the sums are also going to continue to diverge. right? Because if we test these out, we could plug in, let's say if we're looking at pattern 2, if we checked out the 100th term, so we have 1 minus that R value to the 100th, and first term was 100, and then 1 minus 0.5, we're going to see that it's going to, again, continue to get towards 200, right? Approaching up there, right? And we could continue this on if we went to term 1,000, term 2,000. All right, if we were changing this value around, we're going to see that pattern continue. And we're also going to see that for the oscillating one, it's going to continue to diverge, right? So going back to our Shelly sequence, if we start looking at this pattern, and again, we start going towards infinity with this number or 100 terms, again, we're seeing right now a convergence. In fact, it looks like it's converging to about 60, approximately 60, okay? So somewhere in that vicinity, just based on the graph, is what it looks like is happening here. So basically what's happening, if we have an original sequence, go back down here, if we have a sequence and we know that the R, absolute value of R is less than 1, or that it's between basically -1 and 1, right? Somewhere in that frame, think of fractional value less than 1, where R is not equaling 0. This is when we're going to have a converging infinite sum. Okay, so this is your criteria. If you have a value that is less than -1 or bigger than 1, these series aren't going to converge. And basically what's going to happen is we can use our sum formula that we've been using before, and we can simplify it if we're looking for an infinite sum, an infinite series going on forever and ever and ever, plus ... right? Because what we talked about in the last problem is that this value here is approaching 0 in a lot of these, right? It gets closer and closer and closer to 0. So essentially what we can say is we can substitute in here that 1 minus r to the n power, like we had up here, is actually just approaching 1, right? Which means that we can substitute in 1 minus 0, which is just 1, which is going to leave us with a sub 1 times 1 over 1 minus r, which is going to be our sum of the infinite. It's just going to be whatever the first term is, 1 minus r in the denominator, okay? This is kind of that last formula you're definitely going to want to have written down, okay? So we can confirm what we looked at graphically about Shelly's design, because if we're going to keep adding up an infinite amount of terms, the first term was 8, that common ratio was the square root of 3 over 2, and we plug in for r, and 8 divided by 1 minus the square root of 3 divided by 2 gave us right about 60. 59.71 is again right about the 60 that we observed in the graph. Okay. So these are very handy if we are trying to skip over the example A, and if we turn to the last page here, 30, to look here for these sequences that were converging, all right, we can come up with these values. Now note, you can't use the infinite sequence formula on any of these that diverge. So for instance, here, you can't use the infinite sum formula. You can on number 2 because it converged, because that r value is less than 1. You cannot use this formula on number 3 because it doesn't converge. Same thing here with 4, but you could use it on 5, okay? So if we jump back to this last page, if we test this out with number 6, because that was a value that converged, right? Our r value here we said was equal to 0.01 each time. We could take, to find that infinite sum, the first term, 32,000, and then divide that by 1 minus 0.01, right? We're going to get quite a large number here, but 32,000 divided by 1 minus 0.01. We're going to get 32,323 is that value we're converging towards, aka the sum of the infinite series. Okay. Now the infinite series then, if we are going to represent these values as infinite series, we can use again sigma notation. Note, however, like example C shows, our sigma now up top, we're converging towards infinity. So that's how this is going to look a little bit different. So if we are trying to write this as a sigma notation, notice we can write repeating decimals using sigma. And basically what we're saying here is that if we start at term 1, we'll go towards infinity, and then we would have our first term times our r value to k minus 1 power to get this value here. Now, also note, you could have officially written this a second way and say that you started at term 0 and you were going towards infinity. What would have happened is you would have just been raising this to k power each time because you were plugging into 0. So notice these are officially equivalent to each other because you would still be getting the same value in this series. And again, we know it's a series versus a sequence, and that we want to use sigma because of those plus signs. This then tells us we're going to infinity, the plus dot dot dot. All right. Thank you, everybody, and see you in class.